Hey folks, I hope you're doing well. I'm coming to you now to hopefully provide you a little bit of additional support for section 6.4, which gets us to think about the central limit theorem. Hopefully you've had the opportunity to take a look at the videos that I posted in Moodle that somewhat provide you with a snapshot of a sampling distributions of a given statistic. The two given statistics that were mentioned in section 6.3 consisted of a sample proportion, likewise consisted of a sample mean. Section 6.4 specifically notes the distribution of the sampling distribution of a sample mean. X bar is likely the way it was symbolically represented. And if you take a look back over in your e-text in section 6.4, back on pages 266 and 267, they give a little greater detail in the mechanics behind your central limit theorem. So let's talk a little bit about it. It's very simple to work with. Well, first of all, I think it's important for you to understand that it doesn't matter what the shape of the original population is that you're working with. It could be a U-shaped distribution. It could be an exponential distribution. It could be a skewed left distribution. It doesn't matter. We notice a very special pattern about when we take multiple samples from that population of the same size, meaning that when you select samples from that population, you can't change the sample size. It has to remain the same. You could take 100 samples of size 30 and record all those means, and then you'll notice that when you plot them out, they look like a normal curve. They look like a normal distribution. It's a pretty cool phenomenon. It doesn't matter whether you started with a non-normal distribution in your population, but when you choose those samples of the same size and multiple samples of the same size, and you look at how they distribute themselves over the range of all possible values, they make a normal distribution, which really is a powerful idea as we move forward for chapter 7 and 8. So the major assumption that we get to make with the central limit theorem is now we can assume A. The mean of the population, mu, is going to be equivalent to the mean of all sample means, meaning they're going to be exactly the same. 2, we cannot make that same assumption about the standard deviation of all of the sample means. We have to think about it a little bit differently. We have to think about the standard deviation of all sample means as the standard deviation of the population divided by the square root of the sample size. You're like, well, why do we have to do that? Because there's a little pattern that gets observed when we look at the standard deviation of all of those sample means. They change relative to the size of your sample. Meaning, if you were to think about taking 100 samples of size 10, and you took and recorded all those means, you plotted them out in a distribution curve, and you noted what that sample standard deviation would be for all of their sample means. And let's say you did it again, but you changed the sample size. meaning you maybe take a sample size of 50 and you make 100 of those selections. Well, what's going to happen is it's going to change. It's not going to be the same, which is why we have to think about this idea here when we consider the standard deviation of all sample means. So then the question becomes, how do we apply this into a problem? It's really no different. However, you'll notice in your context that when you begin your probability calculations, you're no longer selecting one. You'll notice in your context that you're selecting a group, meaning you're selecting more than one. And you'll also read that we want to know the probability that their mean is at most, at least. The verbiage is still the same, but I'm not selecting one, I'm selecting a group, and I'm looking at what's the probability that their means will be blah, 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 depending upon the context. Point in case, as we're reading back over in section 6.4, just to let you hear the difference in the statements of the problems. I'm going to follow this with a screencastify of some of the problems given to you in my math lab in section 6.4. So stay tuned. Working with limited technology capabilities at this point. So if you were looking on page 272 in your e-text, and let's say we wanted to look at problem number 5. Problem number 5. There on page 5. Oh, take it back to 72. Bear with me as I read aloud. I'm sorry. If you have your computers in front of you, you may find it beneficial to pull the e-text up in Pearson for problem number 5 on page 272. They're asking us to consider an assumption that females have pulse rates that are normally distributed with a mean of 74.0 beats per minute. So they're telling us the population mean. Also, as we read, a population standard deviation of 12.5 beats per minute. Now, 5A, if you look at how the problem is worded, Part A says if one adult female is randomly selected, find the probability that her pulse rate is less than 80 beats per minute. So again, I'm selecting one, not more than one. So when I select one, this is no different than just finding those probability values for the area under the curve using our normal calculators in StatCrunch. It's no different. We insert our mean here, we insert our standard deviation here of 12.5, and we generate that cumulative area under the curve, and that becomes our probability value. However, when we look at Part B is asking us if 16 adult females are selected. So we're selecting not one, but 16, constituting that we are selecting a group. When we select that group, we have to think about can I use the central limit theorem in this case to help me generate my probability value? So in this case, we need to think, A, do we know anything about the original population? In the beginning of the problem, they told us that the normal female population would make the bell curve. So we know that the original population that we're working with is normally distributed. The other check mark that we can use in our favor, if we do not know anything about the original population, is the sample or is the group that's being selected greater than 30? And when that is known, you can still move forward with the application of the central limit theorem to help you generate your probability values. So 5B tells us that we're selecting 16, which obviously is less than 30. But they told us in the opening of the problem that our original population of females, when we look at their pulse rates, the original population of females will normally distribute the pulse rates across the range of all possible values. So, all that said, the original population is normal. So we move forward with central limit theorem. So then you're like, well, what do we do from there? We still use our normal calculator in StatCrunch to generate our probability value. Well, folks, I thought I had my eraser, but obviously I can't find it. I thought I brought it in here with me. Oh well, I'll just use my hand. My silliness doesn't go away just because I have to teach from a distance. Hopefully you'll find this a little amusing. So, when I think about 5B, I know that I can use central limit theorem. I abbreviate central limit theorem with CLT. Can be used. And again, because if you look back in the beginning of the problem, they tell us the normal population of females and their pulse rates is normally distributed. Okay, so we still work with our stat calculators, normal, right? But the mean of the population is also going to be the mean of all the sample means, which was given as 74 beats per minute. But here's where things change. When we think about the standard deviation of all the sample means, we have to take and adjust it. And we adjust it by using the population standard deviation that was given as 12.5, and we divide that by the square root of our sample size, which in this case was 16. And we can simplify this out a little bit. 12.5, right, divided by square root 16, which is 4. You can conceivably key that in to StatCrunch and it'll be fine. You just cannot key in a square root. And in the event that you get a square root value that's not a perfect square, just carry as many decimal places as you can when you simplify out this little instance of standard deviation of the population divided by the square root of your sample size. Stay tuned to a future video where I work with a Screencastify to show you in StatCrunch how one should finish out this problem.